Hello guys, welcome to Physics Grad. This is the fifth video on canonical transformations, and in this video we are going to look at some examples on how we can use the different types of generating functions that we have studied so far in order to construct these canonical transformations. So let us begin and consider our first example. So example 1. So here we are going to use the type 2 generating function f2, which is going to be a function of the old coordinates, new momenta and time, and I am going to define this or assign the functional form as summation over I qi pi. So if I take our f2 to be having this particular functional form, what is the resulting canonical transformation that we are going to get? That is what we are going to see now. So we saw in our previous lecture that if we use f2, then we have the following relation: dou f2 by dou qi must be equal to pi, and dou f2 by dou pi must be equal to qi, and our h dash should be equal to h plus dou f2 by dou t. Now in this case our f2 is not explicitly dependent on time, so this guy goes to 0, therefore we have h dash is equal to h in this case. Also, if we use this particular functional form, this becomes pi equal to pi, and here we get qi equal to qi. Okay, so apparently, or as you can see, therefore this f2, that is when f2 is defined functionally in this form, is the this f2 generates the identity transformation, where we just say that the new momenta is equal to the old momenta and new coordinate is equal to the old coordinate, which is basically multiplying everything by 1, and this is nothing but our identity transformation. Okay, so identity transformation is also a canonical transformation which can be generated using type 2 generating function. So let us take another example, example 2. Here we are going to consider f2 to have a functional form of the following structure, where this is going to be summation over I fi, where fi is a function of the old coordinates qs, where s is the degree of freedom, multiplied by the new momentum. Okay, because our f2 is going to be function of old coordinates, new momentum, time. So this part gives the function of old coordinates and time, and this part gives the function functional dependence on the new momentum. Okay, so now if you see, our relation dou f2 by dou pi will be equal to qi, and this should be equal to fi of q comma t, where q involves all the q1 to qs. Okay, and dou f2 by dou qi should be equal to pi. Okay, now if all our fi's are invertible and independent, then this gives us the point transformation. We have seen already what point transformation is in one of our previous lectures. So if you consider this particular equation, we are expressing the new coordinates as independent invertible functions of the old coordinates and time, which is nothing but what we called as the point transformation. Okay, so a point transformation is also going to be a canonical transformation, and that is why we considered this particular example. So therefore we can conclude that all point transformations are canonical transformations. Okay, that is what this equation tells us. So here we are free to choose whatever the functional form of Fi is, as long as they are invertible and independent, and corresponding to that we will get the point transformation. Okay, where we get Qi as a function of the old coordinate and time. But the expression for the new momenta is, however, not going to be as simple as this. It will depend on the old coordinate, time, as well as the new coordinates Pi. Okay, so that can be got by using this relation plus the fact that our Qi's are related in this manner. Okay, so that was our example 2. That was just to show that all point transformations are canonical transformations. So now let us consider the next example, example 3. Here we use type 1 generating functions and we assign it the functional form summation over I qi. Now we know that f1 should be function of old coordinates, new coordinates and time, and that is what this is. So if we choose such a functional form, then we have seen these relations in our previous lecture. These will give us, this should be equal to Pi, and this is, in fact, if you apply this operation on this, you will get this as Qi. So this is one relation, and dou f1 by dou Qi should be equal to minus Pi, which is equal to Qi, which means that our Pi equal to minus Qi. So here what we are seeing is that our new coordinate has become the old momenta, and our new momenta has become negative of the old coordinates. Okay, this kind of transformation is called exchange transformation, because we are basically exchanging the role, the name, or what we call as coordinate and momenta in our old coordinates, we are now calling them as momenta and coordinates in terms of the new coordinates. That is why it is given the name exchange transformation. Okay, so therefore in effect this transformation interchanges momenta and coordinates, and this emphasizes the independence of coordinates and momenta, which we have already discussed that in Hamilton's formulation, in order to specify the state of the system along a particular path, you need to know the momentum as well as the generalized momentum as well as the generalized coordinate, and in that sense we can say that these two are independent. And this particular transformation, which is also canonical transformation, is showing us explicitly what we mean by that, by saying that even if you swap our or even if you call our coordinates as momenta and momenta as coordinates, nothing changes, which means our initial statement that P and Q are independent is still valid, and there is not much of a difference between Qi's and Pi's except for their names. Okay, all that we can say is that they are 2s independent variables. There is no relation to the to saying that whether that Qi's are actually representing the position coordinates and Pi's are actually equal to mass times velocity. No, that is only true when we consider Cartesian coordinate systems, but when we consider a generalized coordinate system, we say that our Qi and Pi, you should not differentiate them as one representing position and the other representing momenta. No, it is just a name that we give them, but this particular canonical transformation, which is the exchange transformation, shows us that we can even consider our coordinates as momenta and momenta as coordinates. Therefore there is no difference between them. Okay, they are just independent variables. Okay, so this emphasizes the independence of coordinates and momenta. Okay, So this implies that they are both needed to describe the motion of the system in the Hamiltonian formulation, and the distinction is practically in the nomenclature. Okay, so it is just the names that we give them, okay, in order to specify our Hamilton's equation, but other than that there is no difference between them. They are completely equivalent in the sense that you can treat them as independent variables, not assigning them physical meanings like one is representing the physical spatial coordinates and the other is representing mass times velocity. Okay, so this implies they are both needed to describe the motion of the system in Hamilton formulation and the distinction is practically, that is a distinction between Qi and Pi is basically only in their name, okay, is practically in the nomenclature. That is what this statement means. Okay, so therefore we cannot assume Qi represents spatial coordinates and Pi represents mass times velocity. We cannot assume this. Okay. Also, we note the following. Note that exchange transformation can't be derived by using type 2 generating functions. Okay, here clearly we are using type 1 generating function, and this is why we are actually in fact defining the 4 types of generating function, because sometimes we cannot use some generating functions to come up with some canonical distributions, as this is the case wherein we cannot use type 2 generating functions, and that is why we are resorting to type 1. So this is because since Pi is equal to dou f2 by dou Qi, and this should give Pi as a function of only Q, P and T, but here in our exchange transformation our Pi should be equal to Qi, okay, but this relation does not give that. Okay, this relation only gives them in function of old coordinates, new momenta and time, but it does not give Pi as a function of Qi. Therefore we this cannot give this kind of a transformation. Okay, in fact if you take the Legendre transform of the function f1, this particular function with respect to Qi, then what will we get? So take Legendre transform of f1 with respect to Q, then that Legendre transform is nothing but our f2. So our f2 must be equal to f1 minus dou f1 by dou q times Qi, summation Qi. Okay, but our f1, what did we assume f1 as? F1 is basically summation Qi. So this becomes summation Qi minus this particular guy is nothing but, so summation this particular guy is nothing but Qi, which is 0. Okay, so if f2 is 0, this particular guy cannot be found. Okay, so we cannot get a relation for our Pi as a function of Qi, and therefore it doesn't make sense to use f2 in this case, and that is what we mean by saying that exchange transformation cannot be derived by using F2, because such an F2 does not exist which will give us the exchange transformation. Okay, and similarly our identity transformation cannot be derived using F1. Okay, so that is why we need the 4 different types of generating functions, because initially when you look at it, it seems like any transformation, any canonical transformation can be obtained by using just one kind of generating function, but as we saw, that is not always the case. Alright, so let us consider the next example, example 4. So here let us say S is equal to 2, that is degree of freedom is equal to 2. Now if we want the transformation which is Q1 equal to Q1 and P1 equal to P1 and Q2 equal to P2 and P2 equal to minus Q2. So this, if you see, this part is looking like an identity transformation and this part is looking like an exchange transformation. So this is kind of a mixed transformation, and therefore we cannot use any of the 4 types of generating functions alone as such in order to generate such a transformation, but in fact we have to use a mixed generating functions, which also we had seen in our previous lecture. So to get this, we have to use a mixed generating function, which I am going to call f dash. Okay, and our f dash should be defined as Q2 P1 plus Q1 Q2. Okay, sorry, this is Q1 P1 and Q2 P2. Sorry, Q2 Q2. Okay, so if you define our generating function in this form, so if you see, if you compare it with our generating function for identity transformation, so this is our identity transformation. This had Qi Pi term, and here we have Q1 P1. So this should give us the identity transformation for the index 1 coordinates. And if you look at the next one, this is Q2 Q2, that has the form of our exchange transformation Qi, and therefore for that index of coordinates we are going to get the exchange transformation. Okay, so this is a mixture of F1 and F2 corresponding to exchange transformation and identity transformation respectively. So in that sense we say that we need to use a mixed generating function. So if we use this kind of a generating function, we are going to get this kind of a transformation. Okay, so finally let us consider one more example, and here we are going to consider simple harmonic motion. And if we use our Cartesian system, then the Hamiltonian for the simple harmonic motion is going to be p square by 2m plus half kq square. Okay, so this is in Cartesian form. Now, of course, this is a very easy problem to solve. We do not need to perform canonical transformation and solve it, because this is a direct and a straightforward problem. But here this is a good example to demonstrate how we can use canonical transformations to convert from the old coordinates and momenta to new coordinates and momenta, wherein the Hamiltonian is cyclic with respect to some of the new coordinates, and that in turn makes it easier to solve the problem. Okay, of course in this case it is going to look like it is just making the problem tougher to solve, but this is just to demonstrate the power of canonical transformations, wherein we can obtain new coordinates and momenta wherein we can have cyclic variables. Okay, and that is what this example is supposed to demonstrate. Okay, so here we are going to call k by m as equal to the characteristic square of the characteristic frequency, and if we write the Hamiltonian in this form, we will have h is equal to 1 by 2m p square plus m square omega square q square. Okay, now if you notice this is a sum of squares, and if we want to have a canonical transformation such that, for example, our new generalized coordinates should be cyclic in this Hamiltonian, then we can define the following transformation. So if we can have a canonical transformation such that our old coordinates are related to the new coordinates by some function of the new momenta times cos q, and q equal to fp by m omega sin q. Okay, now here we are assuming this is a canonical transformation, and to find this transformation we need to find the form of this f of p, and we are assuming this type of a transformation because if we do this, our q will be cyclic in the Hamiltonian, which means our new Hamiltonian will be independent of q. Okay, now clearly by inverting these relations we can get our p's and q's in terms of q, p and t, but clearly there is no t involved in this sets of equations, so there is not going to be explicit dependence on time, and therefore our h dash should be equal to h, and when we write it in terms of the new coordinates and momenta, this will be equal to 1 by 2m times f of p the whole square cos square q plus m square, let me write it here, plus m square omega square into f of p the whole square sin square q divided by m square omega square. So these will get cancelled, and what we will get is that f of p the whole square by 2m into 1. So clearly our new Hamiltonian does not depend on the new coordinate, and therefore it is cyclic in q. But if our Hamiltonian is cyclic in q, it means that the corresponding conjugate momenta must be conserved. This also we have seen previously. So this implies that our p dot, which is equal to minus dou h by dou q, dou h dash by dou q, since our h dash is not dependent on q, this should be equal to 0, which means that our p is a constant. And since our dou h dash by dou t is equal to 0, this means h dash is also equal to constant in the sense that it is conserved, and I am going to call this the energy E. So from this, now we need to figure out what the value or what is the functional form of f of p. Okay, so how do we find f of p such that we can invert, let me call these relations as equation 1, so that we can invert equation 1 to get canonical transformation equation. Okay, so how do we find this f of p? So from 1, if we divide the two relations, we will get p by q is equal to m omega cot q. Okay, so here I am simply dividing these equations. So from this we see that our p will be equal to m omega q cot q, which here we are expressing it as a function of q and q, and we can say time, but it is not explicitly dependent on time, and we have seen that a generating function of type 1 is in fact going to give us such a relation, because our f1 is going to be function of our old coordinates, new coordinates and time. And if we consider there is no time dependence, and using the relation that dou f1 by dou q must be equal to p, we see that if you compare these two relations, both are going to give p as a function of q and q, and therefore we can say that our dou f1 by dou q should be equal to this guy. Okay, so this implies dou f1 by dou q should be equal to m omega q cot q, making this f1 equal to m omega q square by 2 cot q plus some integration constant c. Now we are free to choose the form of generating function, and we are going to choose the function f1 where this c is going to be 0. Okay, so choose c is equal to 0. So then our f1 is going to be defined by this equation. So if we have that relation, then so this implies that our dou f1 by dou q should be equal to minus p, which is the relation for our type 1 generating function. This means that our p, if you differentiate, so this should be equal to minus dou f1 by dou q. So if I differentiate f1 with respect to capital Q, I am basically differentiating cot q, which will be equal to minus cosec square q, and that minus and this minus will get cancelled, and what we will get is that the new p will be equal to m omega q square by 2 sine square q. Okay, so this will be equal to our new p. All right, so what does this say? This says that if you substitute for, so let me call this, so let me number these equations, that is, yeah. So if I number this equation as equation number 2 and this as equation number 3, okay, so if you substitute, so from here we can say that our q is going to be equal to, so there is an yeah, so our q will be equal to root of 2 by m omega times p into sine q. Okay, that is basically from this equation. All right, so if you compare it with our initial equation, which says that q is f of p by m omega sine q, then comparing these two equations, we immediately see that our f of p should be equal to what? It should be equal to root of 2m omega p. Okay, so therefore by using our generating function to have this form, this particular form, we are able to find what is our f of p, from which we can now write our canonical transformation equations. Okay, so this means that our h dash, which is equal to f of p the whole square by 2m, that is what we derived here. So if we go, where is h dash here? Yeah, so this h dash should be a constant, and yeah, so this is what we got, f of p the whole square by 2m, and that is also what we get here. that is the same relation that I write here. If we substitute for f of p, this we get it as 2m omega p by 2m. So these cancel and this is nothing but omega p. This should be equal to the constant E. And as we saw, our p should also be conserved since q is cyclic. So p is equal to E by omega. Okay. So this is one part of the transformation equation, that is the canonical transformation equation. P is just a constant. Okay. And since so this implies our q should be equal to dou h dash by dou p, and this means that this should be equal to h dash. So dou h dash by dou p is simply going to be omega. So this is going to be equal to omega, sorry, this is q dot. So the Hamilton's equation, this is what it says. So q dot is equal to omega, which implies our q will be equal to omega t plus some integration constant alpha, and this can be determined using initial condition. Okay. Now this implies that substituting q as omega t plus alpha in our equation for small q here, and substituting for f of p of course in terms of energy and omega, what we get is that our q will be equal to root of 2e by m omega square sine omega t plus alpha, which is the well-known solution for the simple harmonic motion in Cartesian coordinate form. Okay. Now of course this might look that this is a difficult way to solve the problem, that is where we are basically overkilling it, but this is just to demonstrate the power of generating functions and canonical transformations, where we can come up with new coordinates wherein we can find some variables which are cyclic, which makes the problem much easier to solve. Okay. And it makes it easier to solve because the conjugate momenta become constant. Okay. And we can simply directly use our Hamilton's equation to find the relation for our new coordinates also, and from there on we can invert back to our original coordinates and find the equations which are satisfied by the correct path. Okay. So that's it for this video. Thank you for watching. See you next time.